Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
For the particle case, epsilon coherent depends on the difference between the particle AP and the matrix lattice parameters. So AP is lattice parameter of the particle, AM is the lattice parameter of the matrix. As shown in the figure, we can write like this: epsilon coherence is equal to AP minus AM by AM. We note that when the particle lattice parameter is greater than that of the matrix, the particle is in the state of compression. Okay. Whereas when the AM is greater than AP, the particle is in tension. This is quite natural. However, both situations give rise to material strengthening, since the increment in strength depends upon the absolute value of epsilon coherent. That is why we said in the previous expression mod of epsilon coherent. Okay, that is straightforward. We will look at the modulus hardening in a deforming particle type. When the dislocation enters the particle having a shear that of the matrix, the dislocation line tension GB square by 2 is altered. The physics here are again analogous to the solid solution strengthening. Since we have already looked at this modulus effect and so on, this is not anything new. But only thing is, we are bringing that idea to the deformable particle concept. Okay. The maximum change in the dislocation self energy, that is when the dislocation is halfway through the particle, is B square R times Gp minus Gm. The distance over which the energy changes is particle radius. Thus, the force proportional to the gradient in the energy is on the order of F is equal to B square times Gp minus Gm, which is nothing but Gb square times epsilon Gp, where on far right side of the equation, G is taken as the matrix shear modulus and the parameter epsilon Gp is Gp minus Gm by Gm is akin to the parameter epsilon G prime used to characterize the modulus hardening in the solid solution strengthening. So it is similar to what we have already seen in the modulus strengthening. So nothing much to discuss here. These are all similar ideas, and you are familiar with all this already. So this is a schematic which shows that the deformable nature. So the dislocation line is there, and it is moving in the matrix, and this is a precipitate, and the precipitate experiencing the dislocation entry, and this is the line tension of the dislocation is altered, and it is maximum when it goes to the distance radius here. So the change in the line segment energy is given by Gp minus Gm into B square by 2 times 2R. That means 2R is the maximum it can cross. Okay, so that is what is given here. So the view looking down on the slip plane as a straight dislocation enters a particle having a radius R on the plane. The dislocation line tension is changed when it enters a particle. The maximum dislocation length affected is the particle diameter. That's what's shown here. It is it can travel from here to here, so to R. The line tension change takes place gradually over the distance equal to R. So the maximum changes can happen here. The change in energy takes place over a distance less than R. This can be considered by substituting B for R to yield a revised equation. So we can also consider the change in energy in the intermediate range, where we can use B instead of R. So F is equal to BR times Gp minus Gm, which is equal to Gb R epsilon Gp. So the associated increase in the shear stress is obtained by dividing F by BL. See, this F by BL also we know. This is a standard equation, that force, maximum force we are trying to find. So tau Gp is equal to Gr epsilon Gp by L prime, which is approximately equal to half Gf epsilon Gp, where F is equal to 2R by L prime. F is equal to particle volume fraction approximate for a straight dislocation. We are simply substituting this 2R by L in this expression and putting it here, and the details of the correct treatment are complex. Again, I am telling you, we are only looking at the semi-quantitative relations and approximate relations. The approximate result to the early stages of precipitation for modulus hardening is tau Gp is equal to 0.01 G times epsilon Gp to the power 3 by 2 into Fr by B to the power half. Coherency and modulus hardening both vary with the mismatch parameter epsilon. This is what is important idea. So the Gp or the epsilon Gp here, and then this epsilon term comes in all the coherency hardening as well as modulus hardening. It comes there, okay. And the epsilon, the parameter epsilon to the power 3 by 2 and with Fr by B to the power half. These two things are the parameters to look at, okay. The values of the numerical proportionality constant in the equations are different for the modulus and coherency hardening. That is understandable. And the next one is chemical strengthening in this same domain. So I am going a little fast because they are all similar idea, but just subtle differences are there. That's why I am just rushing through. But if you look at the equation, they are all similar equations. The parameters are all similar, except the core differences only you have to identify. Okay. So the next one is chemical strengthening. What is chemical strengthening? Same idea. The dislocation is approaching a particle. Then what happens? It enters here and then creates a new surface. Okay, this is a spherical particle, and then once the dislocation enters, the Burgers vector B, and it creates a step here. So that means a new surface is created. So it is within the particle, and an offset B of a portion of the upper part of the particle with respect to the lower part accompanies the dislocation entry, and then once it comes out of this particle, then it creates another step, okay, equivalent to B. A similar offset is effected when the dislocation exits the particle. The complete transit is accompanied by the creation of a matrix precipitate surface area of approximate magnitude of 2 pi r B. So this is very simple, right? So 2 pi r B, the surface area, it is being newly generated because of the edge dislocation entered and then exit the particle. So how does this alter the energy? That's what we are going to see. We are going to bring in the surface energy term into the force. When a dislocation passes through the particle, an additional particle matrix interface is formed as shown in the figure. Since there is a surface energy associated with such an interface, work must be done by the process. So the figure shows the interface surface area is created both when the dislocation enters the particle and also exits. So the maximum force required to push the dislocation through this particle is the maximum value of du by dx of the figure is approximately given by F max is equal to pi r gamma s b divided by b, which is equal to pi r gamma s. So gamma s is a surface energy. This is the schematic which shows a nice idea how this surface energy increases the moment the dislocation enters the particle, which creates the first offset in the front B. Okay, the surface energy increases to this level. Okay, this pi r b gamma s, and then it travels inside and again it exits, creates another surface, again it creates pi r b gamma s. This is 2r is the diameter of the particle. This is nicely shown here. So the energy increase occurs over the distance about equal to the slip vector b. Thus the force required to produce the increase that is proportional to the slope of the energy distance curve is pi r gamma s. So you can just simply substitute this the associated increase in the flow stress is tau chemical. Here we're not saying applied, it is purely a chemical hardening component is given by F max by BL, which is nothing but pi r gamma s by BL prime. L prime is the effective particle spacing. If the dislocation remains straight, we can substitute 2r by L prime, that is equal to F, and then we can rewrite this equation like tau chemical hardening approximately equal to pi F gamma s by 2b. This simplified treatment suffers from shortcomings similar to those of the simplified treatment of modulus hardening. Again, I told you all these semi-quantitative relations will give you some idea about the very specific change in the each of the mechanisms. Okay, the parameters which contributes to the applied stress. That's all we have to look at it. What changes in modulus hardening, coherency hardening, and chemical hardening. What are the new parameters coming to the force balance equation? That's all you have to look for. So the final expression for this chemical analysis is given like this. Tau chem is equal to 2g into gamma s by gr to the power 3 by 2 into fr by b to the power half, which is equal to 2g into epsilon chemical to the power 3 by 2 fr by b whole to the power half. Okay. So we see that the chemical strengthening depending on parameters similar to those describing the coherency and modulus hardening. They're all same. Here you are simply putting epsilon chemical instead of epsilon modulus or coherence. One important point, the strength increase varies with fr by b to the power half, and there is another parameter gamma s by gr for which the strength increases with the 3 by 2 power. Okay. In this sense, gamma s by gr is analogous to both epsilon gp and epsilon coherence, and this is why we have defined gamma s by gr as is equal to epsilon chemical in that equation. So this is all these three equations, empirical equations, though it looks similar, but it gives it brings out that subtle differences, the what way each mechanism contributes to the tau, that is the shear stress, that is the flow stress indirectly. Okay. There are other ways of surface energy or other ways of surface energy can contribute to particle hardening. They are two predominant cases are stacking fault strengthening and order strengthening. So they are also related to the surface energy term. There are two prominent cases, stacking fault strengthening and order strengthening. They are very important. If the stacking fault energies of the particle and the matrix differ, dislocation motion is impeded because the equilibrium separation of the partial dislocation is different in the matrix and particle. So now whatever we have studied in the dislocation dynamics, stacking fault and the partial, when the partials are stable and when they are not stable, all these ideas will come into play, and it's very handy now. Okay. So we are talking about the stacking fault energy difference between particle and the matrix and its consequences on the strengthening mechanisms.